Hello viewers, welcome to add-on. In this question we are asked, what is sampling and derive the sampled output expression with a suitable example, and or what is sampling theorem, that is formula with explanation. Okay, so sampling is a process by which a continuous time signal is converted into a discrete time signal. Okay, this x of t, this is a continuous time signal, and this x of n, this is a discrete time signal. Okay, so the continuous time signal is like this, normal sinusoidal signal. So this is the time axis. So for every values of t, we are getting a particular value. Okay, so this is a continuous time signal where the signal is defined for each and every single value of time. But in the discrete time signal, if we represent the same signal, it will be like this. This is the time axis. So for every values of t or time, the signal is not defined. The signal is only defined for some discrete values of t. Like the time here is 2, here it is 3, here it is 4. So the time here is, so the signal here is defined for the discrete values of t. So this is a discrete time signal, and here the signal is defined for each and every single value of t. So this is a continuous time signal, and sampling is the process by which the continuous time signal is converted into a discrete time signal. Okay, so now what does the sampling theorem states? Sampling theorem states that any band limited signal which is band limited to fm can be reconstructed from its samples if fs is greater than twice of fm. Okay, so to understand the theorem, consider this is a sinusoidal signal. Okay, this is band limited to fm. Okay, so the signal says what? Any band limited signal which is band limited to f of m, which is the frequency of this particular signal, this can be recovered from its samples if fs is greater than equal to twice of fm, where fm is the frequency of this particular signal and fm is the sampling frequency, the rate at which the signal is sampled. So for example, after sampling, the signal become like this. Okay, so the signal become like this. Okay, after sampling, so the theorem states that this signal can be recovered from this signal if the sampling is done at the rate which is greater than twice of fm. Okay, so this is the sampling rate and this is the message frequency rate. Okay, so one thing we need to note, that this sampling rate fs, when it is greater than twice of fm, we can easily do the reconstruction. Okay, this is the case of oversampling. Oversampling means this is a particular points, right? These are the points. If we see in this sampling, if we see the sampled output, we are just taking some particular point or some discrete values from this signal. Okay, so it is just taking a sample values from this continuous time signal to make it a discrete time signal. Okay, so when we do oversampling, we just take more values or more sample point from this signal to construct the sampled output signal. Okay, so this is the case of oversampling. So during this time, if we take the more we take the number of samples, the more it will be easy to reconstruct the signal. Okay, so this is the case of oversampling. And when fs is equal to twice of fm, so when sampling is done at this rate, we are taking exactly that number of samples that is required to reconstruct these signals from this sampled output signal. So in this case, reconstruction is also available. But when fs is less than twice of fm, then signal reconstruction is not possible, because during that time, if we consider the spectrum of the signal, if we consider the spectrum during oversampling, the spectrum will be like this. One thing I need to show before drawing the spectrum is that, suppose this was the actual spectrum before sampling. Okay, this was at I say minus pi, this is pi, this is 2 pi, and this is minus of 2 pi. Okay, so what happens when we do undersampling is that, suppose we are doing the sampling rate like this, fs is equal to, let us say it is fx by 2. Okay, this is the undersampling case. Okay, so what happens in this case? This fx, we know that omega is equal to 2 pi of f. So f is equal to omega by 2 pi. Okay, so if we replace the f by omega, we will be getting omega of s is equal to omega of x, omega of s is equal to omega of x by 2. Okay, so what happens in this case? This is minus pi, this is pi. So when we are downsampling or we are performing the sampling with a factor of 2, so what happens? Omega s equal to, for example, when we are taking pi, so this is our pi. Sorry, when we are downsampling, one thing that happens is the sampling factor will be multiplied, fx into 2. Okay, so it will be fx into 2. So for a particular value which is pi, so it will be 2 pi, and for the value of uh, 2 pi, in this case, in this 2 pi case, the value of omega x was pi. We just multiplied it by 2 to get 2 pi, and similarly here we can see the value is 2 pi. So when it is multiplied by 2, we will be getting a 4 pi. So now the signal spectrum become like this. This spectrum will spread like this. This is from minus 2 pi to 2 pi, and this signal will spread from pi to 4 pi. Similarly, in this section, it will spread like this. This is from minus pi, this is 4 pi, minus 4 pi. So what happens in this case? We are seeing overlapping occurs. This overlapping occurs. So this overlapping is not our desired scenario. This is called aliasing. So when we are trying to recover the original spectrum from this kind of spectrum, we will be getting a spectrum like this. If we recover the spectrum from this spectrum, so we will be getting a spectrum like this. So we can clearly see that this is not our desired scenario. So we need to make sure whenever we are doing a sampling, our sampling rate should be always be greater than equal to twice of fm to reconstruct it from the samples. Now in this slide, sampling can be generally of three types: ideal sampling, flat top sampling, and natural sampling. Okay, these are the three types of sampling. So we don't need to know about the details, we just need to know these are the three types of sampling. And each of these samplings, what happens, this is a continuous time signal, and we will be using a pulse train. So these are the pulses. Okay, these individual straight lines or dotted lines, these are the pulses. We will be using this pulse train. This is m of t, suppose this is g of t. So our sampled output signal y of t, it will be equal to m of t multiplied with g of t. Okay, so this is the pulses. This train of pulses is multiplied with this signal to get our output signal. So this is our ideal sampling. And what happens in the flat top sampling and natural sampling is that in natural sampling, the pulses have a width. Okay, in this scenario the pulses didn't have a width. Here the pulses have a width of tau, and in that case also the signal is get multiplied with this signal. And in flat top sampling too, these pulses are getting these pulses will get multiplied with this signal. Okay, so the difference between the flat top and natural is on the basis of the output sampled signal. So in natural signal, what happens, suppose this is the outline of our message signal. So when we multiply the pulse train with our message signal, the output will be like this. We can see here the top of the pulses, they are changing with respect to the message signal. But in fat top sampling, the top of the pulses will remain the same. Okay, this top of the pulses, they doesn't change. Okay, so that is one of the difference between the natural sampling and flat top sampling. And the thing is, why we have moved on from ideal sampling to natural sampling is that generating this kind of pulse train or impulse train, it's very difficult in practical scenarios. So in order to do sampling practically, we will be using natural sampling or flat top sampling according to our own desire. The only difference in natural sampling and flat top sampling is that in the output sample output, the pulses will change its amplitude, but natural sampling in case of natural sampling, the pulses will change its amplitude or the change the top of the pulses, but in flat top sampling, the top of the pulses will remain the same. It won't change according to the amplitude of our message signal. So this is all for sampling. I think we have all understand that. Thank you.